And I'll start with a quick definition. If we have a square matrix, which I'm calling here the matrix A, then the eigenvectors of the matrix are any non-zero vectors for which the equation ax equals lambda x has a solution. This equation, ax equals lambda x, is a crucial special equation. Later down the page, I call this the Eigen Equation. And it's not exactly clear yet why we would want to solve this equation, but I assure you that this equation is ubiquitous. It shows up in so many contexts and has so many applications. So this equation is a very important equation. What is this equation saying? It's saying that for some matrix A, so I'm going to be given the matrix A, and then my goal is to find vectors such that when I multiply the matrix A times the vector x, I essentially get that same vector x back. Well, give or take this scalar lambda. Let me say that again. A times x yields the vector x back multiplied by some scaling factor lambda. That's not true for all vectors x. In fact, it's pretty rare to be able to find such a vector. And so those vectors get a special name. Those are exactly what we're calling eigenvectors. I'll point out quickly that if the vector x was the vector 0, then this equation would kind of automatically be true. A times 0 is going to equal lambda times 0. That's uninteresting, and that doesn't really tell me anything about the character of the matrix A. So notice that we've excluded that possibility by forcing in my definitions here eigenvectors to be non-zero vectors. So an eigenvector is a special vector that is somehow associated with the matrix A, such that when I multiply A times that eigenvector, I get the same eigenvector back multiplied by the scaling factor lambda. The scaling factor lambda is crucial to this whole equation coming together, and so we give that scaling factor a name. That scalar value lambda is called the eigenvalue associated with a particular eigenvector. So in a certain sense, to find eigenvectors and eigenvalues of a matrix, I simply have to solve this equation. And as I pointed out, it's not clear yet why I want to solve this specific equation, but it will be clear hopefully soon. But as it turns out, this equation is difficult to solve directly. If you want, you can kind of take the perspective that x is an unknown quantity. It's an unknown vector. I don't know what that vector is. At the same time, I don't know what lambda is. Is it true that ax equals 2 times x? Or is it true that ax equals negative 4 times x? Exactly what value of lambda makes this equation true? I don't know. So in a sense, there are two unknowns in this equation, but I only have a single equation. And so in a way, I don't immediately have a form that will allow me to directly solve this equation. So what I need to do, and I've pointed this out at the bottom of the page here, is I need to manipulate this equation a little bit so that it will be in a form which allows me some sort of starting point that I can compute, and then from that starting point I can go back and track down all of the ingredients that I need. Let me show you what I mean. So I remind myself here that our Eigen equation, the equation I'm trying to solve, is ax equals lambda x. And then let me do a little bit of manipulation to this equation. First, as is true in algebra, it's often easier to solve an equation if 0 is on one side. So I'm going to subtract this lambda x over to the left-hand side. Notice that these two quantities on the left-hand side are both vectors, and so when I subtract them, the result will be the 0 vector, not just a scalar 0. Next, it feels like I could factor the x out of this left-hand side. If this were an algebraic equation as opposed to this equation involving matrices and vectors, it would be simple. I would just factor that x out. Since these components are a little bit more complicated, I have to be a little bit more careful. I can, in fact, factor the vector x out. One important property of matrix multiplication is that it is not commutative. So the fact that I have a times x with the x on the right has to be retained. So that's why I factored this x out on the right. And then when I factor it out, it's tempting to write that what I'm left with is a minus lambda. But this is incorrect, because A is some square matrix. It could be a 2 by 2 matrix or a 3 by 3 matrix. Whatever it is, it's a matrix, and the value lambda is, in contrast, just a scalar. It's a real number, -3 or 4 or 6. Actually, it may not even be a real number. We'll discuss those cases eventually as well. But it's impossible to take a square matrix and subtract a number from it. So right now, these are two different types of mathematical objects. So the way that I remedy that is to multiply this scalar lambda by the identity matrix. This is the identity matrix that is the same size as the matrix A. And the identity matrix, I've tried to spell it out in general here, will be a square matrix which has 1s along the diagonal and 0s everywhere else. The identity matrix effectively acts as the number 1 in terms of matrix multiplication. So when I multiply lambda times the identity matrix, I'm not changing the quantity lambda in any way. So now I have an equation here where I've got a square matrix minus another square matrix. So that is defined. That's multiplied by the vector x, and then I get 0. Now we've already pointed out that x can't be 0. Well, actually, if x equals 0, this equation is obviously true. But in my definition, I said that x equals 0 is not a permissible option for an eigenvector. So I'm going to build off of that fact to make an important conclusion. So bear with me here. If x equaled 0, then this system would have exactly one solution. X equals 0 would be the only solution. Since we are not going to permit x to equal 0, that means that this solution will have infinitely many solutions. So, to force this system to have infinitely many solutions, I'm going to force the determinant of this coefficient part. Notice that this whole A minus lambda I is acting like the whole coefficient matrix M. So in order to force this system to have infinitely many solutions, I'm going to force the determinant of this matrix to equal 0. And now if we think about this equation, in this equation, there's actually only one unknown. I know what A is. I was given the matrix A initially in the problem. I know what I is because it's this generic identity matrix, and I can fill in the appropriately sized matrix easily. So the only unknown is lambda. So this equation now has a single unknown, lambda, and so I can solve this equation. Remember, my goal was to manipulate the original Eigen equation in such a way that I would get something which I could actually solve, and we've accomplished that. This equation is not my final answer, but it provides a starting point. If I can solve this equation, that will allow me to identify what lambda needs to be, and then I can return to my initial Eigen equation, or any of these alternative forms of it, and then plug in those specific lambda values to eventually be able to find the corresponding x value. So anytime I'm asked to solve for eigenvectors and eigenvalues of a matrix, I'll always use this equation in the red box here as my starting point. Let me demonstrate that by working through a couple of examples. So in this example, we're asked to find the eigenvalues and eigenvectors of the matrix capital M, given here, a little 2 by 2 matrix. For now, this matrix doesn't really mean anything in particular, but eventually this will be the coefficient matrix of a system of differential equations. And as you'll see in the next section, the eigenvectors and eigenvalues of this matrix will provide the details regarding the key characteristics of the solutions of such a system. But for now, we just want to find the eigenvectors and eigenvalues. As we just derived, our starting point will always be solving the equation where we force the determinant of m minus lambda I to equal 0. Notice that I'm not going to take the determinant of the matrix M itself. I'm actually going to build a new matrix. Let me build that matrix. So this final matrix is the matrix which I will take the determinant of. Just to recap how I built this matrix, I take my original matrix M, and then I subtract lambda times the appropriately sized identity matrix. Here I've used the 2 by 2 identity matrix, obviously. That scalar can be pushed into that identity matrix. And then when I subtract two matrices that are the same size, I just subtract them component-wise. So I have 1 minus lambda, 1 minus 0, etc. So this is the matrix M minus lambda I, and this particular matrix is the matrix whose determinant I want to force to be 0. So let's go ahead and do that. So here I've calculated the determinant of this new matrix, and it's a 2 by 2 determinant. So I multiply these two entries along this diagonal, and then I subtract off the product along this diagonal here. And then you'll notice that when I do that, that yields a polynomial in lambda. In this particular case, a quadratic in lambda. Believe it or not, this is called the characteristic polynomial of the matrix. So once again, we have some sort of overlap with this matrix terminology and the differential equation terminology that we were using earlier in the semester. But recall that I don't just want to calculate what this polynomial is. I want to force that polynomial. I want to force this determinant to equal 0. So the determinant needs to equal 0. And then I can go ahead and FOIL out this polynomial. And if I rework that briefly, I get two values for lambda. Lambda equals -1 and lambda equals 3. So these two lambda values are my eigenvalues. If you take a second to look at the structure of the calculation we've done so far, hopefully you can see that the degree of the characteristic polynomial will agree with or be associated with the size of the matrix. In this particular case, I ended up with a quadratic characteristic polynomial because there were two entries along the diagonal with lambdas in them. You can imagine a 3 by 3 matrix, which would have 3 entries along the diagonal, each with a lambda in it, and that would yield a cubic characteristic polynomial. As such, the number of eigenvalues will always be equal to or less than the number of entries on the diagonal, which is the degree of the characteristic polynomial. And so in this case, the fact that I got two distinct eigenvalues makes sense because the characteristic polynomial will be a quadratic, and as we know, one of the cases is to get two distinct values from solving the quadratic equation. Now that I have these two distinct eigenvalues, I need to use them to find the corresponding eigenvectors. I do this one at a time by picking either of my eigenvalues. Here I've chosen lambda equal -1. And then remember that the equation that I'm trying to solve is ax equals lambda x, or an alternative version has this structure here where I have my matrix minus lambda times the identity matrix times x equals 0. I've already plugged in the specific lambda that I'm dealing with, and actually a second ago we wrote out the matrix M minus lambda I. That was this matrix over here on the right. So what I can now do is return to this matrix, plug in the specific lambda value that I'm considering at the moment, which in this case is lambda equals -1, and then solve the system where that is acting as the coefficient matrix. That whole thing is acting as the coefficient matrix, and then my right-hand side is all zeros. Here's what that augmented matrix would look like. Here I've plugged in lambda equals -1 and 2 spots there. And then, as I mentioned, the right-hand side will be all zeros. I could simplify that, and then using matrix techniques to solve this, I end up with a reduced form of my matrix, which shows me that I'll have infinitely many solutions. Now you'll recall that this whole methodology is built on forcing this system to have infinitely many solutions. So the fact that I have infinitely many here makes sense. And as we demonstrated in example 2, when you have infinitely many solutions, your task becomes to find some relationship between the two variables. This first equation can easily be reworked to say x2 equals -2x1, which tells me that my solutions will have the form x, where I can pick any value I want for x1. To indicate that, I'll just leave x1 as kind of generic here. It's called a free variable. And then once I've chosen what x1 needs to be. x2 needs to be negative 2 times that. And as we saw in example 2, it's notationally helpful to just kind of factor out the x1 that both of these components have in common. And I can rewrite this as 1, negative 2 times x1. So for any choice of x1, if I plug it into that form there, then the resulting vector will be an eigenvector, which is associated with the eigenvalue negative 1. It is a general fact that a constant multiple times any eigenvector is also an eigenvector. And so writing this x1 here is a little redundant. So we always acknowledge that if I was to multiply this vector by any scalar, the result would still be an eigenvector, which corresponds to this particular eigenvalue. So because that fact is true, as I said, writing x1 here is unnecessary. So we'll typically write that my eigenvector is simply 1, negative 2. And I acknowledge that any scalar, any non-zero scalar multiple of that is also an eigenvector. So if you happened to maybe solve this equation in a slightly different way, do you see how you could have ended up with the vector 1/2 negative 1? Well, that would be a non-zero scalar multiple of this vector, so that would also count as an eigenvector. I'll just point out briefly too that there are lots and lots of different notations revolving around eigenvectors, eigenvalues. Sometimes the name of the specific eigenvalue will be listed as a subscript on this eigenvector. Sometimes this will be called x sub 1 because it is the eigenvector associated with the smaller of the two eigenvalues. Lots of different notation. I personally just avoid that and just somehow note that these two things are associated with each other, that this eigenvector is associated with this specific eigenvalue. That's one of our eigenvalues. The other, lambda equals 3, for that eigenvalue, I'll repeat this same process. And you can take a second to verify those steps, but I believe that the eigenvector associated with lambda equals 3 will be this vector here, x equals 1, 2. And again, I recognize that any scalar multiple of that is also an eigenvector. So if you would prefer to write this vector as 3, 6, you're welcome to. If you would prefer to write it as negative 4, negative 8, all of those are also eigenvectors associated with this eigenvalue. So that was our first example, calculating eigenvectors and eigenvalues. Congratulations. And again, we don't exactly know at this point how those tie into systems of differential equations, but we'll demonstrate those details in the next section. For now, we're just practicing this process of calculating eigenvectors and eigenvalues. And speaking of practicing that, let's take a look at one last example, example 4. All right, in example 4, we're asked to find the eigenvectors and eigenvalues of this matrix M. Note that this is a 3 by 3 matrix, so I'll be required to utilize a technique for calculating a 3 by 3 determinant. And as I mentioned, there's a few different ways to do that, but I'll show you my preferred way as we work through this problem. As we saw in the previous problem, our starting point for finding eigenvalues and eigenvectors is to solve this equation, where we set the determinant of m minus lambda I equal to 0. I'm going to skip a few of the preliminary steps that I showed in the previous example. Specifically, I'm not going to write out the matrix m minus lambda I in the several steps that I did in the last problem. From that last problem, I know that m minus lambda I will be the same as the matrix M, but with lambdas subtracted along the diagonal, which means I've got a typo here. Let me fix that. That's better. And now I simply need to evaluate this determinant, and then whatever expression that gives me, I will set it equal to 0, as I already have here. Now when it comes to calculating a 3 by 3 determinant, as I mentioned, there are several techniques, and I'm accustomed to using a technique called Cofactor Expansion. I'll explain the technique as I use it in this example, but if you do need further explanation, I'd encourage you to maybe just Google this, and there's certainly lots of detailed explanations of this process available. Or as always, visit me in office hours and I'd be happy to explain it. The first step in cofactor expansion is to choose a specific row or column. The choice is essentially arbitrary, but it's sort of strategic to choose a row or column that has as many zeros in it as possible. Based on that criteria, I'll choose the first column. Again, if you prefer to use a different column or row but follow the same procedure, you should end up with the same determinant. The entries in this chosen column become coefficients on new determinants. Here's what I mean. Each coefficient in turn, each entry in turn, in this case 1 minus lambda, will become the coefficient on a determinant. The determinant of what? Of what matrix? I'll get to that in a second, but first let me just clarify that the next entry 2 becomes a coefficient on its own determinant, and then the entry 0 becomes a coefficient on its own determinant. This explains why we want to choose a row or column with as many zeros as possible, because these zero coefficients, in this case I just have this 1, will effectively relieve me of the necessity of calculating this determinant, because whatever this determinant is, I'll just be multiplying it by 0. One other important detail that I'd like to mention before I explain what these new matrices are is that part of this method requires that the signs, positive or negative, on the entries that I select to be my coefficients alternate. What that means is that this entry in the first row and first column is assigned a positive value or a positive sign. And so in this expansion, that will be a positive. And then the signs that I need to assign to each value alternate. So since this was a positive, this next one would need to be assigned a negative. So I would have a negative, so I have minus 2 times the determinant here. And then they alternate so that this would be a plus. So I would have plus 0 times this determinant. And that alternation is consistent throughout the rest of the matrix, so that if I had chosen a different row or column, I would use that same scheme to identify the signs that need to be applied to the chosen coefficients. Now, how about these determinants? What am I taking the determinant of? Well, each of these will be a small submatrix of my original matrix. Specifically, this matrix will be the matrix which results from covering up the row and column from which this coefficient came. Let me explain what I mean. I've got the value 1 minus lambda came from the first row and the first column. So I'm going to ignore that first row and that first column. Here I've literally blocked them out. And then the submatrix that results from covering up the row and column from which this entry came will be the matrix which I take the determinant of. So in this case, this little 2 by 2 matrix will be 1 minus lambda, negative 1, negative 1, 1 minus lambda. And I can repeat that process for each of these other two coefficients. So what will this 2 by 2 matrix be? It will be the matrix which results from covering up the row and column that this value of 2 came from. So I'll need to cover up this second row and this first column, and I believe that leaves the submatrix 1, 1, negative 1, 1 minus lambda. Similarly, this last 2 by 2 matrix would be this matrix here. Of course, I don't really need to evaluate this determinant because, as I've already pointed out, I'll be multiplying it by 0, but I write it here just for reference. So now my 3 by 3 determinant has been expanded into cofactors, each of which involves a 2 by 2 determinant. And I know how to calculate a 2 by 2 determinant. I simply follow the procedure we've seen in the recent couple of examples. So as I mentioned, there are several different techniques for evaluating a 3 by 3 determinant, but this is the one that I'm most accustomed to using. And if I go ahead and evaluate those 2 by 2 determinants, I believe I get this expression here. Now recall that there is a 0 on one side of this, and so I need to solve this equation for lambda. generally speaking here, I have a cubic polynomial that's set equal to 0. So this can be a little tricky to solve as well. And so I always keep an eye out for some sort of algebra trick that will enable me to find the roots of this cubic a little bit more efficiently. Here I've worked out the algebra to solve for lambda, and one of the first things I did is I sort of targeted like this lambda minus 2, or I saw that there was going to be a lambda minus 2 here, and then when I simplified and FOILed out this quadratic, I ended up with a lambda minus 2 that I could factor out as well. So this isn't necessarily the cleanest or most efficient way to solve this cubic equation, but I've been able to effectively identify my eigenvalues, and from this step I set lambda minus 2 equal to 0, which of course yields lambda equals 2, and then I could set this quadratic equal to 0 as well, and once I had factored that quadratic, I get lambda equal to -1 and lambda equal to 2 again. So this cubic equation has yielded two distinct eigenvalues, one of them with multiplicity 2. As I said, hopefully this algebra isn't too intimidating and you can kind of identify within any specific problem a strategy to be able to solve for these eigenvalues. Now, as we saw in the previous problem, once I have those eigenvalues, I will deal with them individually. So I'll take lambda equals 2, for example, and I'll plug that eigenvalue in for lambda in the system m minus lambda I x equals 0. That's equivalent to putting that in along the diagonal of this matrix. And then we remember that the right-hand side of the system that I'm trying to solve is all zeros. So that yields this augmented matrix here. And my goal will be to solve however I can. I prefer using matrix techniques, so row operations, but if you want to write this out in terms of variables x1, x2, x3, and do substitution or elimination, that's acceptable as well. For the sake of space, I've left out the individual steps that lead to this reduced form, and I've simply stated the reduced forms here. And even skipping those steps, I'm kind of running out of room here. But I can now unmatrixify, which is to say I can write this in terms of the variables. Remember that these values represent coefficients on variables x1, x2, x3. This represents essentially an equals sign, and then this is the value on the right-hand side. So the first equation tells me that x1 equals 0. The second equation tells me that x2 plus x3 equals 0, and the final equation says 0 equals 0, which doesn't provide any information. So from these two equations here, I'll need to build an eigenvector, and from this second equation, I can see that x2 is equal to negative x3. So I could think of x3 as a free variable, which I could choose any value I want for, and then x2 will be the negative of that. So I could write my eigenvector initially as the x1 entry will definitely be 0. The x2 entry, as we determined here, will be the negative of whatever my choice for x3 is. And then the x3, the third entry, will be whatever that choice is. As we saw in the previous example, I can factor out this variable, write this as simply 0, negative 1, 1 times x3. And then we know that any scalar multiple times an eigenvector is an eigenvector. So writing this x3 is redundant. And I can simply write that the eigenvector is 0, negative 1, 1. Next, I need to find a little room somewhere to be able to perform a similar calculation for my other eigenvalue, lambda equals negative 1. I may just be able to squeeze it in this last little section of space here. Once again, I plug in the specific lambda that I'm dealing with into the equation m minus lambda I x equals 0. The minus lambda in this case gives me a minus negative 1 or a plus I, and that yields this augmented system. I have once again skipped over the specific steps required to reduce this matrix, but this is the reduced form. And now if I write these rows in variable or equation form, first row tells me that x1 plus 3 halves x3 equals 0. And the second equation tells me that x2 minus 2x3 equals 0. And it's not hard to rework these such that x1 can be rewritten in terms of x3. x2 can be written in terms of x3, and x3 can also be written in terms of x3 by simply saying that x3 is equal to itself. So, acknowledging this sort of step that I always do here where I write out the vector and then I factor out the variable, and then I just keep the vector itself, recognizing that the scalar multiplier here is redundant in a way. Let me see if I can just go ahead and write out what my final eigenvector would be. I think it would be negative 3 halves 2, 1. And of course, any scalar multiple of this vector would also work as the eigenvector. So if I didn't like this fraction, I could easily multiply each component by 2. Either way, I have barely squeezed in the calculations necessary to find the eigenvector associated with the eigenvalue of lambda equals -1. This is kind of an interesting case because my characteristic polynomial is cubic, that is, it's to the 3rd degree, because I'm dealing with a 3 by 3 matrix, and yet I only have 2 eigenvalues, and each of those values produce essentially one distinct eigenvector. And so while I kind of expected to have 3 eigenvalues and 3 eigenvectors, I really just have these 2 eigenvalues, lambda equals 2 and lambda equals -1, and then the 2 corresponding eigenvectors as indicated here. So that completes section 5.3. In this section, I tried to point out some fundamental preliminary facts about systems of linear equations, and then the goal was to understand how to calculate eigenvalues and eigenvectors for a given square matrix, as we've demonstrated in these last 2 examples. In the next section, our author gives a real basic introduction to some fundamentals about systems of differential equations. And in the section following that, we'll actually take a look at how to use this linear algebra technology, these techniques, these methods to solve systems of differential equations.